So particle states. Today we're going to talk about what a particle is. And as usual, I have this bad habit of rushing the lecture at the end. So I just go very, very quickly, and next time I have to clean up. So hopefully I'll do less of that in the future. But let me start with a review of spinors. Very quick review of spinors. We're just talking about this. The restricted Lorentz group in even space-time dimensions is SO plus D comma 1. In odd space-time dimensions, SO D comma 1. This is a connected group, which is not necessarily simply connected. In D larger equal to 2, it has a twofold cover. Its universal cover is a twofold cover. It's a Z2, and that's the origin of the spinors, right? Because you could go around, pick up minus sign, go around twice, and pick up 1. And those give you projective representations. So the idea was that representation of the universal cover give you the projective representations of the group. And when these two, the universal cover has the groups, the fundamental group is Z, so you have funky statistics. And when these 1, the connected part of the Lorentz group SO plus 1 comma 1 is connected and simple connected, but you could still have spinors, not really in the sense of spinors that we have in higher dimensions. All right. It's a 2 cover of R. There's a trick. If anyone's interested, I can explain it to you guys. All right, good. This group that we're talking about, we often call it spin plus D comma 1. Okay, this is the cover, the double cover. Sorry, by definition, spin plus D comma 1 is always a double cover, right? Even in 2 dimensions. So spin 2 comma 1 is SL2R, right? It's a double cover. It need not be simple connected. Okay, I said that. Now, what was the Lie algebra? The Lie algebra of Euclidean, we said we used it, the Lie algebra of the Euclidean theory to argue for left and right spinors. That is SO4, SO3 comma 1, you return SO4, and spin 4 is 2 copies of SU2, SU2 left, SU2 right. This might sound fancy. What it is you had in Poincare in the Lorentz group in 3 plus 1 dimensions, you had rotation matrices and boost matrices. You constructed this complex linear combinations of them, NIs. And what you obtained was 2 commuting copies of SU2s. This is the SU2 algebra, 2 commuting copies. That's what it means to say SU2 left, SU2 right. Pay a lot of attention to the signs and those NI plus minus. Today we're going to talk about that a lot. Okay. Now, the representation theory of this, because there's 2 copies of SU2, you already know how to talk about its E-reps. J left, J right? Right? And J is a half integer, right? That labels the spin of each representation. We can have 0, 0. It's a Lorentz scalar, half 1, or 0, half. These are left and right while spinors. They have 2 complex components, side 1, side 2. Oops. And then you have the Lorentz vector, which is a half-half representation. All right. I said all of this. Then we said, okay, how do you make sense of this representation theory a little bit more high level? This is more convenient. So I try to go through the details of it. I don't know, actually, give me feedback about this for the next time. Most textbooks on quantum field theory, they just start define Dirac matrices as things that satisfy this algebra, and then blah, blah, blah. I don't know if the song and NAS was useful or helpful. I found it useful, but later, give me feedback. I could cut it out of the next time I teach QFT. So Dirac algebra or Clifford algebra is the algebra of matrices that satisfy these relations, right? And they could come in various dimensions, right? And then this is their anti-commutator. Their commutator up to I over 4, we're gonna call sigma tilde mu nus, which are the elements of the Lorentz Lie algebra. That's basically it. The elements of the Lorentz-Lie algebra are the anti-commutator, are proportionally anti-commutators of the Dirac matrices. Good. So a Dirac spinner is a four-dimensional vector, right? But these are all internal. These are like spin directions, right? These are independent complex components. There's a top in chiral basis. You put a left-handed spinner, a two-component complex vector here, and a right-handed spinner with this notation of raised alpha dot up there for convention down here. Then we said that this satisfies the Dirac equation, which is gamma mu del mu minus m prime psi equal to 0. For the simplest action we could write down. Then Majorana spinner in Dirac notation is a particle that the left-handed and the right-handed component of it is just built out of the left-handed one. We're going to give these names today. One of them we're going to call the particle. The other one we're going to call the antiparticle. Right? So Majorana, in this new terminology we're going to be using, is a particle that is its own antiparticle. Is a spinner that's its own antiparticle. That's a Majorana spinner, right? So what is the antiparticle of a scalar field? Itself, right? So this is Majorana is about spinners. Okay. We introduce what now while spinners written in the basis of Dirac basis look like, you know, just a left-handed, no right-handed guy. The right-handed while is like left-handed 0, right-handed something. And the way we constructed this was out of the projections, P left, P right. Do you remember how the projections were built? Right? Yeah. Okay, good. So that was a review, very crash review of what we discussed last time. Today, what are we going to talk about? We're going to talk about two things. We're going to say that elementary particles, single particle. This is something I did not specify. And single elementary particle is an irreducible, a unitary, irreducible representation of the Poincare. So this is a subspace of the Hilbert space that furnishes a unitary, irreducible representation of the Poincare. We're going to go over that today. Okay. Well, I just briefly mentioned it last time, rushed through it, and probably butchered it. Second, if we have time, I'm hoping that we have time, we're going to go through the solutions of the free Dirac equations. And I'll point out two things. You'll notice two important things. You're solving an equation for vectors that have four complex components, right? There will be two pairs of, there will be a pair of solutions. Each of them will have two complex components. One of them we're going to call the particle, the other one we're going to call antiparticle. U and V. Keep that in mind. We're going to talk about the properties. Good? All right. So what's an elementary particle? I said this before, but a single elementary particle, we don't have, in quantum field theory, we need not have the notion of particles. But if you do have a subsector, if you have a sector of the Hilbert space that transforms irreducibly under the Poincare transformation, thus we say that that is a single particle. Let me just skip all of this because I think, oh, well, up to a point. Okay. Is this familiar? I want to argue that this is familiar. Imagine quantum mechanics of a single particle. A non-relativistic free particle. You were solving the Schrodinger equation. Here is what it was, right? And the solutions of this Schrodinger equation, this is a free particle, was e to the power of IPX with e, which is p squared over 2m, right? And you called the Hilbert space as the Hilbert space was score integrable functions. Sorry, yeah, school integral functions of P, right? Oh, actually, yeah, I had a little bit of a different point here. Messed up. All right. How do I want to say this? Two things. I said before that a particle that you use representation of Poincare group, keep that in mind. I'm going to introduce a separate notion that is familiar from the fact that you were solving the Schrödinger equation. You found these plane wave solutions, then your wave function, then your symmetry transformations. Sorry, your wave function was a score integrable. A single particle was score integrable function over those eigenkets, right? So that's what the one particle Hilbert space was. You identify a bunch of eigenkets, right? And then you integrate over them with score integrable function. Keep that in mind. We're going to use this. Actually, I'm going to make one more. Yeah, we're going to use this to build representations of the Poincare group. One little trick you could do here. So your function was your wave function was an integral included an integral over P, right? Only position. We didn't integrate over P0 in quantum mechanics, right? You could have, if you introduce a P0 integral in quantum mechanics and put in a Dirac delta function that forces the unshell condition. You could have, right? Because what you're solving the time independent Schrödinger equation. If you're looking at the evolution of these eigenkets, they would all evolve by e to power minus I energy of momentum P over h bar, and that energy of momentum P would be P squared over 12. Yeah.
But you have to write down the position basis with which you write the wave function. But we don't have a position basis in quantum theory.
Well, here I'm just making a statement about what one particle was in quantum mechanics. That's all I'm saying. That's all I'm saying. Of course, there's another direct analogy, right? So a wave function over there was we found the eigenkets, and we integrated over these eigenkets using phi of P. Do you know why we did that? Because there were symmetries that would transform. Well, okay, sorry, I should not. I'm loud. It's all good. So the point I'm making here is that there's a score integral function worth of things that we put over momenta, over the eigenkets that we put in, and then you could have written the integral over P as an integral over two-dimensional P if you put a Dirac delta function. Okay, let me not make any further statements. So what are we going to do? What we're going to do is we're going to be building unitary, irreducible representations of the Poincare. What's important is that I'm talking about subspaces of the Hilbert space. Otherwise, there's no reason to insist on unitary. Right? So what is the Poincare group? In homogeneous Lorentz group, some people call it. It's just SO plus D comma 1, add to it the translations. The way we're going to do this is through two steps. The first step is very similar to what we just did for the single non-relativistic particle. We have an operator. So here what we had was a Hamiltonian, which was e to the power of, which was P squared over 2m, right? And the eigenkets of it were kets P. Here what we have is that we have a ket P, and we're going to define an eigenket for it, right? P mu acting on some vector in the Hilbert space is P mu acting. This Hilbert space is the Fock space. It's like the whole thing, right? So these are very, very special states. That's why the name of this lecture is particle states. These are special vectors in the Fock space. They're all describing a single particle. Good. So now if you apply a, like a translation, it will just pick up a phase, right? So these are analogs of my ket p's in quantum mechanics. What did I do next? I just took these ket p's and integrated with over all momenta in space and time, putting the unshell condition. I'm gonna do the exact same thing here. I'm gonna integrate my psi p squared over all momenta with two unshell conditions. One is that p mu minus m squared has to be 0. That's the analog of E equal p squared over 2m. I wrote it covariantly. I'm doing this because I want it to be covariant. Second, what was the interpretation of P naught? Energy. It better be positive. So I'm going to put a, whatever is that called? Heaviside function. Right? This is my integration measure, which you can tell there's a Dirac delta function here. So you can remove one of the integrals. What do you get if you remove one of the integrals? This is an important identity in quantum field theory. Peskin goes through this in gory detail. What you get is an integral over the spatial part of the momentum. You pick up 2 over energy, absolute value of energy, if you integrate this. You could do things using the left side to remain covariant. You could do integrals like the right side is not covariant because you have picked time-space splitting. In canonical quantization of quantum field theory, we're going to do the right side. If you want to do path integrals and like generic covariantly, you'll be using the left-hand side expression. But they're equivalent expressions.
What guarantees is that there exists this momentum eigenvector?
What guarantees that? Well, okay, anyone. If your theory has a particle, there would be, right? But nothing guarantees any of this stuff, right? But actually, no. Wait a second. No. Let's just say that. Well, it's pretty straightforward. Take a vector, right? That then apply Lorentz transformation. It will move or Poincare transformation. It will move you around in the Fock space. Hopefully, you will eventually cover a subspace and not the whole thing. That would be a representation. Then you would start block diagonals and make it diagonal. Okay. In this sense of things, actually, all the theories we know have these particles. Single particle, not particles. That was the wrong term. All right. So just the way to think about this unshell condition is that the fact that the norm of the momentum vector, this is just the statement that it's just the Einstein equation, right? Equal mc squared. That's the stat expression written covariantly. And the fact that you want the energy to be positive, P0 to be positive. Everyone's familiar with this? By the way, one more thing. Okay. Maybe I should have said this. In the quantum mechanics case, you had a symmetry. What was the symmetry?
Unitary symmetry.
Well, there was a symmetry. Translations. Right? Translations was a symmetry. And what is a symmetry group? Well, actually, translation in time and space. So the group is abelian. Its irreducible representations are one-dimensional, and that's what they are, ket-speed. Right? Time translations acting on this ket-speed is just multiplied by phase. That's all it is. Right? What did we do? These were EREPs. You basically said, I'm going to take a reducible representation, integrated, added a whole bunch of these representations. The action of time evolution on one of these wave functions is diagonal. Good. All right. Similarly here. Here, what is the abelian group we're talking about? It's the RD comma 1. That's what we're diagonalizing. RD comma 1. Good. So if you want to know, if you want to understand, I could have said this from the beginning. If you want to understand the Poincare group, the representations of it, first take the abelian part, diagonalize. That's what that is. Any questions about that? I just have to give you a second part and tell you what, then you will be done. This is a general rule about a methodology for constructing representations of the group. If you're given a group, first find the largest abelian subgroup of it you can, diagonalize that, right? I'm hinting at some structure, deep structure in group theory, but here it's pretty obvious, right? All right. What's the next step? The next step is something that goes with the name of the little group. It's something very, very simple. If I have the ket p mu, oh, sorry, not ket p mu, I call it psi p, right? So this is the eigenket. If I have this ket, how can I explore this, all these different momenta that were satisfying p mu minus m squared equals 0. So remember the p space, you had these two conditions, right? So these corresponded to the parabola, this guy and this guy, and the positive energy one is this one, right? Sorry, the surface, right? So to go from one such momentum eigenvector to another momentum eigenvector, how do you get there? Sorry?
Exponentiation.
What group transformation you have to do to change the momentum of that? Boost. You boost it. Right? That's all you need to do. What does boost do? You move at a point, you start at a point, it will change your p mu, preserving this condition and the positivity. So it moves you around this parabola, upper parabola. The same analogy holds in the quantum mechanics. None of this is quantum mechanics. What is a transformation that changes your p? E to the power of I alpha x. Because x is just del v. And the reason that I integrated over all values of p is that because those I could get everywhere. Right? So what the idea is that you apply a lambda mu to this p mu and get a new one, right? So you send your p mu to this guy. And this way you explore this wave function worth of this structure that I was talking about. Good? However, the Lorentz group is large. Not all Lorentz elements. Pick one of these vectors. Not all Lorentz elements would change p mu. Some Lorentz group elements, when they act on the psi p mu, they will keep it as p mu. The p mu will not change. But you will have to operate. You will have to act, right? Sorry, is this clear? There will be parts of the. There will be transform. I think I have this here. Yeah, this equation. There is a subgroup of the Lorentz group that, given a vector p mu, will leave that vector in there. It's called the little group. Let me give you an example. Here is p vector. This is a p vector. M0, 0, 0. Which part of the Lorentz group preserves this vector? Give me an example of Lorentz group. Huh? Rotations. Right? Good. So the fact that this rotation is a Lorentz transformation. It is represented on the Hilbert space as a unitary. So the unitary acts on the ket, not changing p mu. What does that tell you? It means that this ket will have to have extra indices. Could have extra indices. And this could act on those extra indices. But not necessarily, but it could have extra indices. Without changing p mu, it could act on those extra quantum numbers, whatever the hell they are. Right? So what I'm arguing is this. If you want to construct an irreducible representation of the Poincare group, you first look at a function worth a wave function that is integrated over this function condition. You have to, next to that, you have to find an irreducible representation of the little group. Those two together will give you a representation of the Poincare. Those two together will give you a representation of the Poincare. Good. Now we're going to go through this in detail. Actually, what is the? Okay, that's my next point. So that's what the little group is in physics in general, right? A little group in physics in general is this. You have a group, say, I don't know, name a group, SUM comma n, right? That acts on vectors that are n plus n dimensional complex numbers. Pick one such vector, and then you could define a little group for that vector. It's the stabilizer of it. Mathematicians call that the stabilizer, the subgroup that preserves that vector. Can you see where I'm going with this? No. I said all of this. What I'm gonna say is this. Let me tell you in advance what the story is, and then we'll go through it. There is a distinction in little groups of different vectors. If this is a vector that's supposed to describe the p mu of an actual physical particle, its corresponding m squared better be non-negative. Right? There are two cases that occur that are different. If m is 0, you get a separate little group compared to the case where m is positive. Massless particles and massive particles will have distinct little groups. This is the story. That's very important. Right? That's where we're going. And the analysis is going to be very simple. What is the little group? So if I have a massive particle, what's the distinction actually? Can anyone guess what the distinction is between a massive and massless from the point of view of this analysis? Can you guess it? Well, actually, deduce it. If I have a massive particle, I can always sit in its rest frame, which means that I can always turn it into this vector. A massless particle has no rest frame. When I turn it into this form, what is the little group of this vector? Which is SO3. Done. So the little group for these guys is always SO3. If you have a massive particle, the way you construct your representation theory of the massive particle is you pick an era of SO3, but hopefully you know exactly what it is. What is it?
J.
Exactly, J is because it's the double cover of it is SU2 and it's just J. So how would you write, label, put the quantum numbers for an irreducible representation of the Lorentz group? You put m squared J JZ. This is a representation for massive particles. However, for massive particles, they can change. So what is this now? Now I just described it in this frame, right? Now, if I have a general vector p mu that satisfies this condition, but it's not in this form. It's not in the rest frame. How do you describe the list? What is the analog of the rotations, SO3? It's still SO3, but which elements of the Lorentz group is it? Let me do that. Consider, sorry, a p mu, which is time-like and is on this surface. That has a name, I'm forgetting. You could write this down. Okay, I'm going to give you the fancy version. So I want to do the fancy version. Let me see. No, let me not do the fancy version. No. I think I'm happy with the rotations. But let me just remind you. Previously, I called this n plus minus, right? These combinations of j plus ik over 2, right? In this context, I'm going to call them j left right, because now you know what left right are, and you know that that had to do with left spinner and right spinner. Remember that the vector is also a half-half representation, and this is the action of the left mover, and that's the action of the right mover. This is how it was a half-half representation, right? So what are the rotations? Rotations correspond to j left plus j right, right? Hopefully that's clear. If I add j left and j right, I just get the rotation. So j left plus j right, these guys are the little group. They generate the little group, SO3 worth of the little group. If you want to know what are the other elements, that change your K, your P mu? Boost. For massive particle, boosts are the only things, right? Because rotations don't change your P mu at all. It's trivial. Right? What are those guys? They're just boosts. What are they? They're j left minus j right. But this analysis now is covariant. So what you're doing is really you're looking at, yeah, okay, I said what I said. A massive particle is labeled by the following quantum numbers: m or m squared. M is a positive number. J3. I call it Jz. Okay, J3. This has to do with the representation of the diagonal SU2. Diagonal SU2 is another name for rotations, right? And this has to do with the mass. So this is written in the basis that is diagonal. If you want to find it in a basis that's not diagonal, you apply boost to this vector, right? And you know how boost transforms, acts on thing. So this will be generically P mu and JJ3. Right? Any questions about massive particles before we get to massless? So this is the representation. So these are massive particle states as vectors of the Fock space that describe a single massive particle. Any questions about that? I know that I'm already doing quantum mechanics a little bit, but I think you guys are okay with quantum mechanics. Questions? I'm doing well with time today. I don't know why. That's uncharacteristic of me. Maybe I should go on more on like tangents. Okay. Next is a massless particle. Usually I do not go on tangents if I don't know the topic well. All right. Here's a you go to the, and I apologize. I think I said I'll try to stick to a signature throughout the whole course, but I'm pretty sure I've switched my signature already a couple of times. So here's a massless particle, right? Maybe my signature original that I started with was minus EE. I don't know. Okay, so this is EE00. This is a massless particle. I can bring a massless particle always into that signature. Signature, that form. So if you're asking what is the little group of this, well, it's obvious that rotations in the 2-3 directions is in the little group. So that's J1, right? Because remember, rotation in the 2-3 direction, we said that generated is J23. Then we use this epsilon tensor to label it by things that keep the direction that's preserved, that is fixed under the rotation. So that's J1, that's obvious. What are the guys that keep this fixed? You could convince yourself of. Here's my attempt at doing it. I suggest that you think about these matrices, Lorentz transformations. K3 minus J2 and K2 plus J3. These are the guys that fix this vector. All right, what's gonna happen next is somewhat exotic, even to me. I don't have a very deep understanding of it, but it really follows the same structure of what we've known before, right? For massive particles, it became this a square integral function over the eigenkits of this with the unshelled condition, and then representation theory of SU2 that you know back and forth by now, right? Here, it's going to be a representation theory of a group that you're less familiar with. And I will not have time to discuss it well because I don't know it well. All right, but I'm just going to give you pieces of the story. All right, so here's J1. Let's call A K2 plus J A, and B is K3 minus J2. What are the commutation relations that follow from the Lie algebra? A and B commute. I don't know if you can see that already, but they commute. J1 and A give you IB, J1 and B give you minus IA. This is algebraically the same as R2 semi-direct product of SO2. If that doesn't tell you anything, sorry. That's the Lorentzian, that's a Euclidean 2D Poincare group. All right, so this is the Lie algebra. Is everything about the Lie algebra clear? If this A and B was ending up being something proportional to J1, that would have looked like SU2, but it's not. All right, it's another group. The way you turn this into something that you recognize is by introducing A plus minus, which is A plus minus IB. This way, A plus and A minus, they commute, and J and A plus is plus A plus, J and A minus is minus A. Do you recognize some of it at least? Do you recognize this representation? This is something that I think you should recognize, well, hopefully recognize. Would they call it A plus? Plus A plus? Sorry, A plus. Yeah, that's right. Do you have any examples of this on the film? Huh? SL2. SL2. You might be right about that, actually. I do not know.
There's +2 A plus in SL2.
Huh, maybe. I have a different name for this, but like from things that you recognize from physics. To describe this, I can talk about classical physics and some transformations on a line. Take X, take P to be translations, generative translations. J would be scaling. If this is a scaling operator, and this is a translation, we satisfy this relation. With scaling, so X sent to lambda X. What is a generative scaling? E to the power of minus XLX. Something, S. The generator is XLX. Right? So just do this. X del X del X. Well, did I get the minus sign? Yeah, I think I got the minus sign. So it's minus del X. Oh, sorry. Do you see it or do I need to do it? Good. So it's the same algebra as scaling and translations. You have two copies of this, right? What is the other copy? If you pick, well, okay, sorry. Now let me make this a little bit more obvious. Take 1 plus 1 dimensional space, time. Remember that I said I can always bring a vector, trivialize 2 of the direction. So I'm effectively working with 2-dimensional space-time here, right? Think about boost. How does the boost act on X plus? How does boost act on X plus? Oh, this is not. X del T plus, minus, plus T del X. Right? If I write it in terms of X plus and X minus, it becomes X plus L plus, X plus L plus minus X minus. It acts like scaling.
X plus is your time masses.
It just scales this, right? This flow, this boost over here, scale. Scale. Good. How does boost act on this guy? Scaling, now this direction. What are your 2 translations? P plus and P minus. So what did you end up with? You ended up with, well, this algebra, sorry. The Lie algebra, sorry. That's sort of where my intuition stops. The rest of them, I'm just going to say some algebra gibberish. All right, so that's what the group is. Up to here is intuitive. Hopefully. Are there any questions about this part? Remember that effectively I got rid of the J1, right? Like that trivializes the other 2 directions. That's obvious. Hopefully. Yeah. All right. So now we want to construct a representation theory of this. By the way, oh, I'm so sorry. I could have said this way earlier. You know, a representation of like this in basic quantum mechanics, this group in basic quantum mechanics. Simple harmonic oscillator. What is the name of this? Number operator. What's this commutator? What does a number operator do? It reduces n by 1.
The number?
I'm not beginning the signs wrong. As usual. It's the same algebra. No, but this is correct. So it's the same algebra. So now, based on that, you should expect the representation. Okay, now I actually take my words back. I know this pretty well. The representation of this should be very familiar, right? What do? You look at, well, no, it's a little bit tricky, sorry. It's not that obvious. Because the reason is that here A and A dagger do not commute. But in the example that I had A plus and A minus, and they do commute. But it's somewhat analogous. Here, to build a representation, we take the kets that are killed by A. Here, you also take kets, what do you want to call them? I call them lambda. That are killed by A plus and A minus. Sorry? Yeah. And what is lambda here? I also want them to be an eigen operator, eigenvector of J1. But J1 commutes with those guys. I can also do that. Right? Oh, sorry. What did I say? No, it does not. No, sorry. That's incorrect. Sorry. What do I say? Thank you. Thank you. No, it does not. It does not. Thank you. So this is the eigenoperator. I told you I don't understand this properly. Thanks for the correction. It turns out, I haven't argued this, but it turns out that the representation theory of this requires lambda to be half integers.
Why?
That's a statement about representation theory, I do not know. But I can point you to where to read about this. The absolute value of lambda is called spin. Lambda has a name. It's called helicity. So previously, the way we labeled our kets for massive particles was P mu and SU2 representation, J and J3. Here we're labeling it with P mu and lambda. Lambda is a half integer. And the analog of J spin is the absolute value of lambda. So if I give you lambda, I've given you both. A photon has helicity P mu plus minus 1 and no lambda equals 0 states. At some point in this course, I'll explain the counting of the degrees of freedom of photon in a very, very intuitive way. This is not how I understand it, and I will not be able to explain why. Maybe next time I teach this course, I either remove this statement, well, I should not remove it, but I'll try to explain it intuitively. I do not understand this statement, this language. Any questions?
Massless particles, we are labeling them with P mu and lambda.
Helicity, yes. Helicity and P mu. If you have a massive particle and helicity for a spin half particle, sorry, for a spin one particle is +1 minus 1, not 0. Right? Some of these guys are removed. For a spin half, you have +1 plus half minus half. For spin 1, it would be just +1 minus 1, no 0. The example that we will be working with in this whole course is always going to be spin 1, it would be photon, and we'll explain why lambda equals 0 if not there. Spin 2 would be graviton, right? That also has a bunch of these lambdas removed. All right. But hopefully it's clear that if I'm describing to you a ket of a graviton, I should tell you helicity, what helicity is, yeah.
So, okay, just to recap, we have the Poincare group.
Yeah.
We have massive particles which can go to a restaurant.
Yeah.
Build those representations via going to the little group.
Yeah.
And with the
Well, we'll label it using M squared and J and JZ or J3 and a function worth of P mu's integrated, right? Like function over P mu's. That's a generic particle. That's a generic.
then we reason.
That's a reducible representation. Hopefully it's clear. The moment I say P mu, phi of P mu, that's reducible. Because that particle is just a billion.
And then reason repeat for the massless part.
For the massless part, you label it using you just said it. P mu and lambda.
Yes.
Yeah, that's basically what you do. And then a function worth, and again, the part of it that is like you integrate over all the allowed P mu's, that are equal to 0.
This method can be repeated for any group.
And we have a motivation to construct them, yes.
Oh.
It's, group theory representations, that this philosophy I described is more general. That's what you're asking. Yeah. All right. In the remaining, if there are questions, ask now. In the remaining 15 minutes, I'm going to switch gears and talk about solutions of the Dirac equation. So these are what particles are for us. In a free theory, what are two particles? What is a ket in the Hilbert space that's two particles? Exactly. If the particles are indistinguishable, you have to symmetrize. If they're distinguishable, if they're indistinguishable depending on whether they're fermions or bosons, you have to symmetrize, anti-symmetrize them. Now you could ask me, how do you know if you symmetrize or anti-symmetrize? Spin statistics theorem tells you it's not up to you. If it's spin integer, you have to symmetrize. If it's half integer, you have to anti-symmetrize. We're going to prove that. In quantum mechanics, it's all arbitrary. In quantum field, I did not say that. In quantum field theory, it's just in your face again. It's really limited. All right. Okay. Sorry. Quick question. The ket, which is a symmetrized particle 1 tensor particle 2, exists in even in tracking theory, right? But what is a manifestation of interaction? What's special about free theories? Yeah, but what's the manifestation of it in this language? What's the most important fact of a free theory you know? Sorry, no interaction. What does that mean? What does it mean that I have two particles that don't interact?
There's no combinations.
Yes.
Basically two separate equations.
Yes. Even classical. It just means that energy of the system is E1 plus E2. Right? Which means that if you prepare this state in an energy eigenstate, this state is an energy eigenstate, the tensor product symmetrized is an energy eigenstate. That's a free theory. And in tracking theory, it's not an energy eigenstate, it's some complicated mess that you don't know anything about. So it makes sense in free theory to talk about two particle states, and in tracking theory, right?
So like the tensor product states that you construct are like the eigenstates in the free particle.
Yeah.
And then they're not.
Yeah. Yeah. They're not even like, like if a state is not, we're talking space-time, if the state is not stationary or anything, right, it's not very sensible to talk about it. right?
So, like, something that is common in quantum optics is that they'll like write down rest states, like
Mhm.
what prevents you from trying to like construct a group algebra using those things?
So the rest state, sorry, what do you mean by the rest state? I want to make sure that we're talking about something.
Like, just like you like tensor the Fock states with the number states, like, so like if you have a two-level system, you'll have like 0, 1, and then you'll have like a bunch of Fock states. And then like when you,
Oh, so you're talking about something that's unfamiliar to me. I thought I knew what it was, but I'm not sure.
like, so like if you have a single like atom cavity and then like many photons, you can like, the eigenstates aren't like, the eigenstates like a Hamiltonian of like, that says like, oh, like the photons switch, like the photons either like raise the atom state or kill the atom state and then like create a photon or annihilate a photon. Like those are your interactions. The dress states for that are obviously not like the eigenstates of the three, where it's just like, you know, like one out of one thing.
Yeah. That's the thing. If I understand correctly, what you're talking about is very similar to dressing in quantum field theory. Well, it is quantum field theory. Quantum optics is quantum field theory. Yeah, but let me not comment on it because I did not understand all the aspects of it. But I would say one thing. Photons, right? Our theory of photons is a bunch of non-interacting harmonic oscillators.
Yeah.
Right? So it has properly that property. You could talk about a single photon, 2 photon states, energizing states, right? For an interacting theory, that's a mess. Okay, I'll not comment on this further. We'll come back to this. We'll have to talk about the attractions, but for now, it gets deeper into the quantum mechanics of it, and I don't want to do that for now. We're almost reaching the end of classical story, but let me do a little bit of free Dirac equation. All right, now to change gears. Are there any last questions? Sorry, I did not butcher your. Any other questions before I switch gears? All right. So solutions of the free Dirac equation. Here is two things happen here that I want to highlight. I want to highlight that the fact that spinors came out of the representation theory, came out of projective representation of the Lorentz group. So it was in our face, we had to introduce them, right? And this dynamics was also forced upon us by locality and all the principles of action we discussed earlier in this course. This is all classical. So we have to take this equation seriously. This equation is the equation that predicts that every particle in nature must have an antiparticle. There's no way quantum mechanics could have done that. This is field theory. But that's something that is just forced upon us in field theory. And then I'll highlight this one particular aspect of this is that there will be a notion of a charge transformation, which is a Z2 symmetry. Sorry, transformation, need not be a symmetry, which swaps particles with antiparticles. Right? Once I say what the particle is, what an antiparticle is, we could also swap them and see if it's a transformation we could do. And the question is, would the theory or equations remain symmetric under it or not? Good. So that's what I want you to pay attention to. It might get a little bit messy, but I want you to pay attention to that. All right, this is the equation I want to solve. There is a very, very cute trick to doing this. You might have heard this. Well, okay, let me first do it. This is a first order equation. First order equations are somewhat non-dynamical. Let me not go on a tangent because I don't have much time. But if you take this, it vanishes, multiplied on the left by I gamma mu del mu plus m. What you get is something minus m squared. That something is this operator squared. That is the D'Alembert. So there is a sense in which you can construct something that looks like Klein-Gordon-ish here. And that's what we're going to use that. right? But this is something for you to check. This is just from everything that you know, you could check this identity. Dirac operator, which is sorry, sometimes they write a D slash. That I gamma mu del mu, that thing, is something that, roughly speaking, squares to the number. Good. That's very important fact. It's like a square root of it. There's a sense in which spinors are square root. Well, I don't want to push that. So let's try to solve this. What are the solutions going to look like? They're going to have 4 complex functions in them. All right. So what is the solution of this? This is this. If I Fourier transform this, this is p mu plus m squared equals 0, or I forget already. There's a plus minus. I already screwed up my convention of minus and plus. The unshelled condition. p mu plus m squared equals 0, right? Now that we're solving for that, there are 2 choices, p0 positive and p0 negative, right? I'm gonna pick p0 positive because energy needs to be positive. However, I always have this solution, e to the power of I p mu x mu, e to minus I p mu x mu. P0 of both solutions are positive. There are no negative energies here, right? And then it's a second order differential equation, so I put 2 functions, UP and VP. The idea is that UP solves this equation, is killed by this guy. VP is killed by this guy. These are called positive modes. These are called negative modes. And hopefully remember that these guys are each, they have 2 complex function worth of degrees of freedom. I can write them as four vector notation, but they have 2 complex functions in them. So we'll go through that. All right. As usual, this is a massive particle. Let's sit in this rest frame to make life easy. So P0 mu is M0, right? So this equation just becomes M gamma naught minus M U of P0. So I'm solving this equation, right? This is gamma mu. U P0 mu is equal to M. Oh, I'm just writing what this is, right? Is it clear what I'm writing? So when I by the way, hopefully this is clear. When I write I gamma mu del mu minus M, this is a 4x4 matrix. So this is M multiplied by 4x4 matrix. Hopefully that's implied, right? So that's why I have M minus identity coming from this term. M gamma naught gives you this I. Why is that? Because this is what gamma mu is. Sigma I, sigma 0, sigma bar 0. They're both identity. The difference was the sign of the sigma I. That was good. Okay, so this is a question I have to solve. Well, that's pretty straightforward, right? Here is the solution for it. Square root of M C. And the normalization convention is that C dagger C is 1. For example, pick this vector to be 1, 0, this vector to be 1, 0. Good. This solves that. Now, what is the interpretation of this 0, 1 versus 1, 0 versus 0, 1? The interpretation, which I encourage you to work out, I do not have time to fully explain, but I'll try, is that the 1, 0 is a particle that has spin up along x3 axis. If you take a spin up particle like this, you could boost it, right? And what it would do is that it would bring your 1, 0 to something that looks like cosh eta sinh eta. Yeah, it gets I'm getting used to, and as usual at the end of the lecture, I'm rushing it. But let me just very quickly say this, that a generic, hopefully I argued for this, right? This is a solution of the Dirac equation. And then next, what I do to it is just a boost. This generates another solution. I picked a particular boost in the along the x3 direction, but I could have picked in any directions. So in most general form, I can write this vector in this way. There are two linearly independent solutions here, 1, 0 and 0, 1, and write them as CS. This is what they are. You can put these in the Fourier transform Dirac equation and see they solve it. That's what we did. Just did. So what are those complex functions worth of things that we're talking about? They're functions of this P, right? Because we first Fourier transform, we have to Fourier transform back. Actually, I'm running out of time, and I'm halfway through this. Let me try. Okay, so this is my UP. This is the solution to the positive mode, and it's a convention to, like you could talk about U dagger U. You want to normalize your ket properly, right? And a convention that's useful is taking the normalization of U dagger U, U bar U. U bar is just dagger gamma naught. Remember that that's the way that we're constructing these. That was a convenient notation in the for spinners in the Dirac context. Our normalization choice was C or zeta, whatever it is. Dagger zeta is 1. So U bar U is 2m. These are solutions to the Dirac equation with positive frequency. This is all I said so far. And U has two linearly independent solutions for S1 and 2, and this is how they look like in most general form. As a 4 vector, right? Sorry, vector with 4 components. Good. And this is the normalization. Notice that this part is just built canonically using sigma s. So there are only 2 degrees of freedom here. Right? Now, similarly, there are 2 degrees of linearly independent solutions for V of P as well. You just repeat the analysis that I just did. Now the distinction is that this is plus now, right? And what you obtain is Vs of P. These are the vectors, and this is a normalization choice that we pick. Let me not explain the sum rules because I'm out of time. But let me just pause here and just wrap up. We're going to come back to this next time. So what did we see? Very quickly, we took Dirac equation, right? Massive spinners. We tried to solve for it very quickly. We found 2 sets of solutions. We call them positive frequency and negative. Sorry, maybe I shouldn't use that terminology. One of them was multiplied by E2 minus P mu x mu. The other one was E2 plus I P mu x mu. But P mu is always on shell, right? Including the P0 has to be positive, right? The coefficients of each of these guys are 4 vectors. However, they have 2 degrees of freedom independent, right? One way that we wrote them, what are the 2 degrees of freedom? This is how I was writing them, right? This is for the U guys, this is it, right? Oh. And then for the U guys, the bottom part is built from the top one, right? Similarly for V part, but the way you construct it is different. This is one particular solution, you apply a boost to it, it remains a solution. Exactly why? Okay, think about why it remains a solution. And we constructed these guys. We'll come back to this next time. U is a particle, V is an antiparticle. And the fact that we always end up with particles and antiparticles is a statement about their gamma matrices. That would look like, it's a representation of the Lorentz group. Yeah, I don't have time to go say anything further. Are there any questions? Last questions. Well, make a big deal out of antiparticles, as we should, because they're a big deal. All right, let me just say one thing, because I don't think that I went on enough tangents today.